What are constitutional isomers?
Same molecular formula.
Okay, so yeah, same molecular formula, right? Except they all have different connectivities, right? So for example, if I wanted to draw a couple of the constitutional isomers of hexane, I could go about doing that with our bond line structure, right? So we've got 1, 2, 3, 4, 5, 6. So that's a hexane, right? When we go about trying to find all of these various constitutional isomers, so if I said draw all of them for the C6H14, how should we go about doing that now that we're drawing stuff in bond line structure, right? So for me, I draw usually the straight chain version first, right? But now I can probably just pop off one of these groups and just start to put it at different positions, right? So let's say I take off this little methyl at the end and I put it at this position, right? So same exact thing, I can move that methyl to the middle guy, right? So now, at this point in time, if I move it to this position, I'm going to get the exact same molecule, okay? So now I'm going to say, okay, I'm going to take off another little portion of this, and I'm going to put it off of here as well. So that's another thing I can do is, nope, wrong one, is take off another guy and put it off here as well, okay? Now, there's an issue at this point in time, okay? When we start to draw these guys in these bond line structures, sometimes it's hard to see whether or not we've actually drawn the same structure, right? So at this point, this guy and this guy are exactly the same, right? So I've drawn the same thing over, so I haven't drawn, let's say, all the constitutional isomers of C6H14. How could I easily be able to pick or know whether or not I've actually drawn the same structure, whether or not these were the same compound or constitutional isomers of each other, now that we know about our nomenclature? If they're the same compound, what are they going to both have? The same name, right? So a nice little trick that they always try to throw in here is they'll have you look at two molecules and say, are these the same compounds? And the only way you can tell is if they have the same name. If they have the same name, then they're the same compound. If they don't have the same name, then they're constitutional isomers of one another, as long as they have the same molecular formula, okay? So we're going to do a problem like that. Also note that as we increase the molecular formula of these guys, what happens to the numbers of possible constitutional isomers? It just exponentially increases, right? So going further from here, we're going to stick with these guys quite a bit, but just note that as these guys get bigger, the ways that you can arrange them with the same exact molecular formula increases dramatically, okay? So again, how would I have known whether or not those two guys were constitutional isomers of one another, or whether they were the same structure? I would have named them, okay? And so when we went about naming them, we would have found that this guy was 3-methylpentane, and the other one that I draw was also 3-methylpentane. If they have the same name, they are the same compound. If they don't have the same name, then they're different. If they have the same molecular formula and not the same name, then they're constitutional isomers of one another, okay? Okay, so same name, same compound, different names, but the same molecular formula. That's when you have these constitutional isomers. Okay, so let's try that. I have two different compounds, and I want to know, are these the same compound, or are they constitutional isomers of one another? So we went over this one in class. First kind of little bit of trying to answer this question is naming both of them, right? And so we want to name a compound. First thing is to find the parent chain, the longest consecutive string of carbons, right? So for this first compound, we'll call this guy compound A. We have a chain of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I had gone up this route, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that wouldn't, if I'd gone up this route, that would have been 9, which is not the longest chain. So we have our parent chain of 10, and the parent chain of 10 is a decane. Okay, so then once we do that, we want to identify the substituents. So right now we've got a methyl, so a methyl, a methyl, methyl. Then we've got 1, 2, 3. This is a propyl. So propyl and 3 methyls. And so now we need to number our parent to make sure that our first substituent gets the lowest number possible. So we start over here, 1, 2, 3. Our first substituent comes in the 3 position. Or if we start over here, 1, 2, 3, 4, 5, the first would be in the 5. So starting on the left is correct. So then we'll move to 4, 5, 6, 7, 8, 9, 10. So now we're ready to assemble. So we have 3 methyls, so that's going to be trimethyl. M comes before P in the alphabet, so those methyls will come first. The first one's at the 3 position, the second one is at the 4 position, and then the third one is at the 5 position. And so then that's a dash trimethyl. And then we have our second substituent, or second class, or second type of substituent, the propyl group. That's at the 6th position. So this is 3, 4, 5 trimethyl, 6 propyl. And then we have the parent name, so decane. Okay, so that is the name for that guy, which is hard enough. Now as we move over to the right, we're going to have 1, 2, 3, 4, 5, 6. If I keep going, 7, 8, 9, 10. Okay, so we have a 10 carbon chain here. This is decane again. Then we have, let's see, a methyl. And we have a methyl, we have a methyl, and then we have a 1, 2, 3 propyl group. So now we're going to number. We've got I always forget that. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So same thing. We've got a 3, 4, 5 trimethyl. And then we've got a 6 propyl. And then we've got our parent, decane. So because they have the same name, they are the same compound. If you had named them and they didn't have the same name, but they had the exact same molecular formula, then you would have had a constitutional isomer instead. So now we're briefly going to talk about the relative stability of different isomers, and then we're going to move forward talking about Newman projections, okay? All right, so we just drew, or those two guys, are they're different isomers of one another?
Yes.
So we're going to talk right now about if we have a bunch of different isomers, how can we know who's going to be more stable, okay? So what do I mean by stable? I say that a lot, and I don't necessarily know if we always know what I mean by that. So in general, the more stable a molecule is, the less reactive it is. Okay, so when I talk about stability, what I'm really looking for is lower in energy and less reactivity. Energy, less reactivity. So it's a great drawing day for me. Very good handwriting. Okay, so we're looking for lower in energy overall, less reactivity. Anything that's more stable is always going to be less reactive. That's the whole entire purpose, okay? All right, so now, how are we going to assess the relative stability of these alkanes? So what we do quite frequently, especially with a lot of our hydrocarbon-type compounds, is we will undergo them, or we will put them through a combustion reaction, okay? So let's say that we had that. Let's say that we start with an octane molecule, so C8H18. And let's say that this is a completely straight chain octane, right? So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, okay? What we're going to do is we're going to take this octane and we're going to combust it, okay? So in a combustion reaction, what do we combine this guy with? Oxygen, so molecular oxygen, so O2. And then the products of all of these combustion reactions, especially when we're dealing with these hydrocarbons, are carbon dioxide and water. Okay, so our two products here are going to be carbon dioxide and H2O, okay? All right, so what we can do at that point in time, after we undergo this combustion reaction, is we can measure the enthalpy of this reaction, okay? So remember that enthalpy is delta H, so we'll write enthalpy, okay? And this delta H for this octane, straight chain octane, ends up being about minus 5,470 kilojoules per mole, okay? Okay, so now what else have I not, or I failed to do up here in my overall reaction? I didn't balance it, right? So when we balance these, we end up with about 8 of these guys. We end up with 9 of these guys. And then in a lot of these reactions, we can go ahead and have fractions of our coefficients. So it ends up being about 12 halves oxygen. Okay? All right, so now let's go back to this idea behind enthalpy, right? So I said this is kind of like the heat of the reaction, right? So these reactions are all very exothermic. How do I know that they're exothermic?
Negative.
The negative sign on enthalpy, right? So this guy being negative tells us it's exothermic. So it releases all of this heat to the surroundings. How do we usually measure enthalpy in terms of the energies of our products and our reactants? What does delta always mean? It's final minus initial, right? But in terms of products and reactants, who does that relate to? It's going to be the enthalpy of our products, right? Our final state of the reaction of our products minus the enthalpy of our reactants, okay? Okay, so now we can kind of draw that on a nice little energy diagram, okay? So we're still looking at this combustion reaction. If I have a negative value for this delta H, who has a higher enthalpy? Who has a higher energy? My reactants or my products? Again, if this is a negative value overall. Yeah. The reactants, right? Because these guys with the negative in front have to be larger so that overall the sign here is negative, okay? And so I can go ahead and draw that nice little energy diagram, right? Let's say we have enthalpy over here. Okay, and I know because this is exothermic, the energy level of my reactants are going to be up here. So this is our octane. And then the energy of our products is going to be down here. And so this is our 8 CO2 plus 9 H2O. And again, this difference in energy right now is that delta H. It is that minus 5,470 kilojoules. Okay? Okay, so now what am I getting to? What's the purpose of this? Okay, we can take this guy and we can do the exact same thing, except we can maybe use a different isomer of this octane, right? So let's say that we do the exact same reaction for a different isomer of octane. We'll say it's this guy, right, with our nice little oxygens going to make our CO2s plus our H2Os. And we can, again, measure the enthalpy difference or the enthalpy evolved in this overall reaction. So for this guy, we end up getting a minus 5,452 kilojoules per mole. Okay, so a couple things to note. This guy and that guy have the exact same molecular formula. Okay, so when this balances out, we're going to get the exact same products overall. So this is going to end up being our nice little plus 12 halves oxygen. This is going to get 8 CO2s. This is going to be 9 H2Os. Also compared to this guy, what is this relative to that? That's what I would call a straight chain isomer, right? Because it's just a branched straight chain isomer. This guy comparatively is a much more branched isomer, right? So there are a lot of branches in here. It kind of looks like 2 tert-butyl groups put together, okay? So now, if we try to put this guy onto our little energy diagram here, where is it going to be relative to the straight chain isomer up top? Because now the products are the exact same. They're going to have the exact same energy difference, but relative to that 5,470, what is this value?
It is.
Is it less than the 5,470 difference in energy, or is it greater than?
Less than.
Less than, right? And so because these guys are the exact same, but overall the energy involved in this reaction is less than the energy involved in the first one, this branched isomer falls at a slightly lower energy level. That energy difference is smaller overall, okay? So this guy ends up right here, and we get an overall energy difference of the 5,452, or whatever it was. Yeah, 52. Okay? So what's the moral of this story? We had a straight chain isomer, we had a branched isomer. Who is lower in energy, who is more stable? The branch. And it's always the case. Branched isomers are always more stable, they're always lower in energy than the overall straight chain isomers. So the more branching, the more stable the molecule. And again, we know that via these combustion reactions, because we can reproduce this in the lab, and we can find that the more branching overall, the lower the energy, the lower the overall heat of reaction. Maybe I should get this ready. I think I still have them together. Okay, so that's it with respect to constitutional isomers. We're now going to move in to a fun topic that always loses people, which is dealing with different conformations about our alkanes. Okay, so before we can talk about conformations, and what I mean by conformations is arrangements in three-dimensional space, we need to talk about how to draw our molecules correctly so that we can see the various conformations that they're going to take on, okay? So we're going to start with the most simple of our alkanes that we can actually talk about this with, which is ethane. So what is ethane? Eth is how many carbons? 2, right? So 2 carbons. What are the other bonds to the 2 carbons probably? Just the hydrogens, right? So if I wanted to draw the bond line structure of ethane, that's it. It's just a line, okay? Now, again, when we draw bond line structures, when we draw things with that nice solid line, we're assuming that those things are in the same plane, okay? So if I have 1 carbon here and I have 1 carbon here, all the other bonds of those carbons are hydrogens, right? So one of them I can draw in the same plane, and the other I can also draw in the same plane, because what type of geometry do we have about this carbon? What is our molecular geometry here? Carbon, it's got 4 bonds to it.
sp3.
It's sp3 hybridized, but what is the molecular geometry? It is one of these guys. Tetrahedral.
How has
Right?
that 4 bonds?
4 bonds to carbon is tetrahedral overall. Okay, and so again, it's tetrahedral. If we have a nice little model like we do here, what I've drawn right now is one of the bond is in the same plane as the other bond, but what's happening with these guys? If these two are in the same plane, this 2-dimensional plane here, one of them is now pointing out at you, and one of them is going away from you. How do we depict these guys?
Do you have dashes?
We have the dashes and wedges, right? And so for ethane, it's just a carbon to a hydrogen. These bonds are all in the same plane. The other 2 hydrogens, one's coming out at us and one's going into the board, and then one's coming out at us and one's going into the board, right? That's how we depict tetrahedral carbon via our bond line structures. We have to use the wedges and the dashes. So just as a reminder, what does a wedge imply?
In front of you?
It's coming out towards you, right? And what does a dash imply? Going back into the board. Into board or sheet or whatever you're drawing on. Yes.
And it's always opposite of the 2? Like you...
Yeah, so again, like if this guy and this guy are that part that are here, right, then these 2 have to go down. They're both pointing away from what we just had in the same plane, right? Does that make sense?
No.
Hold on. So for this guy, let me try to put this together. This is essentially our molecule, right? Right now I have 1 hydrogen that is in the same plane as the carbon-carbon bond with the other hydrogen. This guy is now pointing down, coming back. This guy's going out. This guy's pointing up, going back. This guy's coming out, right?
Okay.
So we are trying to maintain that appropriate tetrahedral structure for everything. If there's a line, it's in the same plane. And there can only be 2 bonds that are in the same plane. The other 2 have to be coming out and going in.
So I can never draw it with the line through this, with the 2 on top and the both?
No. Yeah, no, we don't usually draw like that. You could, in theory, but we usually will not. Not with bond line. Okay, so that's, again, to just reacquaint you with the bond line structure, right, and how we represent tetrahedral carbon. Now what we're going to do is we're going to rotate this, okay? So we're gonna take our nice little pretty ethane molecule and our nice bond line structure, and we're gonna rotate it 45 degrees. Okay, so we're gonna take this guy and we're gonna rotate 45 degrees. And what we're gonna be left with is something called the sawhorse structure. Okay, so in the sawhorse structure, it looks like a sawhorse, I think. I don't even really know what a sawhorse is, but I think it does. We have this guy up front, which is our front carbon that we don't draw, right? We have that bond connecting the two to our carbon in the back, okay? Now, this is nice because you can see everything, but it's also very difficult to draw. And so we want a nice, easy way to draw these various projections that we need. And so what we're going to do is we're going to take the sawhorse structure and we're going to rotate it again 45 degrees. And we're going to be left with what is called the Newman projection of this molecule, okay? So I'm going to explain, we're going to draw a Newman projection, and then I'm going to explain what each part means and how I want you guys to go about drawing this, okay? But again, we've taken ethane, we've rotated into the sawhorse projection, now we're rotating again 45 degrees to get it into our Newman projection. It's all the exact same molecule, it's just different ways to draw it, okay? Okay, so let's go about drawing one. You guys get an idea of how we're going to do this, okay? So now when we draw these Newman projections, they love to draw creepy eyes to try to show you what you're looking at, right? So note, you will either be given some creepy, strange eye or an arrow pointing down what bond axis specifically they want you to focus on, okay? Again, I have redrawn the slight sawhorse projection for that ethane molecule, okay? So now, they're wanting us to look down this way. If we have this guy here, they're wanting us to look this way at it. What we're going to do in our Newman projection is we're going to draw that front carbon first, okay? And so what we do is we start by drawing, let's say, a little dot to represent that front carbon. If I'm looking down at this guy this way, and that's my front carbon that I'm looking at, what's going directly down? A hydrogen, right? So I'm looking this way, there's a hydrogen pointing directly down. So I'm going to go ahead and draw that. We've got a hydrogen here, right? Now where are these two hydrogens going? One's out to the right and one's out to the left, if I'm looking at this guy this way, okay? So I'm going to go ahead and draw one out to the right, one out to the left, okay? So this is the front carbon that we are looking at, okay? Okay, so we're still creepily looking at this guy. The thing about the Newman projection is when I'm looking directly down this carbon-carbon bond axis, do you see the back carbon? No, right? And so because of that, we don't really get to implicitly draw it. Instead, what we represent the back carbon as is a circle in the back, okay? So the big circle is our back carbon. And front carbon is just a little dot in the middle, okay? So again, we're looking through this bond to our back carbon at this point. What is pointing directly up on that back carbon? Another hydrogen, right? So we've got this guy points directly up. I'm going to draw that on my back carbon. We've got this guy, one hydrogen pointing directly up. And now what's pointing off to the left and to the right?
More.
Two other hydrogens, right? So they're going to go on my back carbon as well. We have one pointing to the right, one pointing to the left. Okay? This is the Newman projection for ethane. Newman projection. Okay? So there's a lot of little bits and pieces to it. This is also the point in time where it is kind of helpful to have a model kit with respect to organic chemistry so that you can visualize things a little bit better, right? I would look for something cheap, like these little Darling model kits if you're super interested in it. Not the nice expensive ones that come with the big thick balls, because those actually are quite useless. So something nice and cheap like this, okay? Okay, so ethane, super easy. Let's get a little bit more practice by drawing maybe a little bit harder molecule and drawing the Newman projection for it, okay? So, yes?
Do we have to worry about the sawhorse?
No.
Okay.
It's just showing you how we get it into the Newman projection. Okay, so same type thing here. we've got a molecule, right? This is one of our alkanes. How many carbons do we have in this molecule? We have 4, right? So we've got 1, 2, 3, 4. What bond are they wanting us to look down, right? Where is the arrow pointing at right now? The second carbon, right? So there's a couple of options here, and this is what I'm trying to give you guys a heads up on. They can do this. They can point directly at the carbon and the bond that they want you to look down, or they can also say, I want you to draw the Newman projection looking down the carbon 2 to carbon 3 axis, right? So they can just give you the molecule and say, draw the Newman projection looking down the carbon 2 to carbon 3 bond axis, okay? That's essentially the same as giving you this arrow pointing at carbon 2. So Newman. There should be some sort of, I'm sure there is some sort of Seinfeld reference to these Newman projections. Okay, so we're going to start with our front carbon, right? That front carbon, what different substituent does it have on it right now? So this is our carbon 2, this is what we're looking at. What is this group?
Carbon.
It's a carbon, but most importantly, it's a methyl, right? So there's a couple different ways that we can call this. We can represent this as a CH3, that's fine. We can also say just ME, methyl, okay? What about this guy? What is this doing right now? It's coming out at us, so that's bromine. We'll just leave it as bromine. What is implied now? The hydrogen, right? So the hydrogen is not going to be drawn for you. It's implied, but where is it going? Right? Is it in the same plane? Is it coming out at us? It's a dash, right? It's a dash and it's going back. So that's your responsibility to recognize that, okay? Okay, so now I'm ready to draw my front carbon. If I have my little dot representing it, who's going to be coming down? This thing, right, which we could say is a CH3 group or a methyl group. Who's going to be pointing up and to the right? The bromine, right, because we're looking down this guy, bromine is pointing up and to the right. And then who's going to be pointing up and to the left? Hydrogen. So that is our front carbon. Yes.
So for the Newman, I don't have to write the dashes or the
Yep. It's all being like, again, we're looking at it like this.
okay.
This is what we're seeing. Straight lines only. Okay, so then after we have our front carbon, we're ready for our back carbon. So I'm going to draw a big circle, right? Now for our back carbon, who is pointing up out of that circle?
CH3.
This is another methyl group, right? So we can write CH3 up here. Now coming back to this back carbon, who is pointing down into the right now at this point? Bromine, right? So bromine's coming out at us. It's going to be coming to the right. Bromine. And then, again, who is implied that's pointing down into the left? Hydrogen. Yes.
So does this only work when it comes to, like, when you're looking at it from a carbon, like, that goes straight, you can't do, like, multiple carbons, I guess?
You can't do multiple carbons. Like, if this had another carbon group at it,
Okay.
that wouldn't be a methyl group, now it would be an ethyl group. That would be...
Okay. So, so you can only do it with methyl?
You can only do it with between two atoms. You can only put down one bond at a time.
Okay.
Yep.
If the bromide in the bottom had dashes as opposed to the wedge,
Mhm.
I would put it like when I do the Newman where the bottom H is.
Yeah.
Okay,
So
like
if it's
it's
dashed
going
and
to the
going down, then it's going to be going to the left as we draw this. We're looking at it, it's coming to our left. I can go ahead and draw the H. What?
That would be
What would you do for a lone pair?
You put it in, it would be just another bond.
Okay,
So like if there was like a lone pair here instead, then I would have put a lone pair there.
Oh.
Okay, all right, so two parts to it. Front carbon. First off, you have to orient yourself to make sure that you are seeing everything correctly. Once you've done that, identified the bond that they're wanting you to look down, you're going to draw the front carbon first, with just our nice little Y shape, and then that back carbon is going to be represented by that big circle in the back. Okay, so I've got a couple of different examples here of different molecules where I want you to draw the Newman projection as viewed down whatever bond I'm indicating, and I'm trying to indicate that via an arrow. Again, I could draw some sort of creepy eye to show you as well. I don't draw eyes well though, so that's what you get. I think the arrow is better anyways, but if you want to imagine the eye, then please do, okay? All right, so we did these in class. I'm going to go over them now. I'm going to start with this first one on the left, which is A, we'll say. And they want us specifically to focus on, I'm going to highlight the bond. So this bond, right? This is kind of the bond axis that we're looking down. So I'm going to start with my front carbon, so this guy. And I'm going to go ahead and draw it as a nice little dot, right? Now, if I'm looking at this, and I've turned my body to actually look down this bond axis, I've got one group that is going to be pointing down, and that is a methyl group. So there's a couple ways that we can represent that. We can say CH3, right, which is the molecular formula of it. It's an ugly CH3, so we're going to replace that. So CH3. Or we could also synonymously use methyl. We can just write Me. So either or. So Me. Again, if we continue to look down this bond, if this guy is coming down, then this one is pointing out into the right, right? So we're pointing up into the right. It's also a methyl group, so we can just write Me. And then we've got this guy who's pointing up into the left. So we can draw that guy pointing up into the left, so methyl, okay? So that's our front carbon. Again, we're looking down this axis. So we're going to represent our back carbon as a circle. For our back carbon, we only see one group. It's pointing directly up as we're looking down this way, so we can go ahead and draw that. That is, again, a methyl group. And now, of course, there is an implied hydrogen here, and then a hydrogen here, right? So for this hydrogen, as we're looking down the sky, it's going to be pointing down into the left, or pardon me, the right. And then the back hydrogen, the one that's going into the board, is going to be pointing down and to the left for our Newman projection, okay? So I'll try to make the second one clear. That was kind of an ugly projection. Okay, so for the second one, same thing. They're wanting us to look down specifically this bond, okay? And we're going to start with this guy being our front carbon up here, so this carbon. Okay, so as we go about this, I'm going to draw that front carbon first. Now, what we have attached to that front carbon is a 1,2 carbon chain, right? So 2 carbon we can depict as CH2CH3, just the molecular formula of that. We can also just call this an ethyl group, right? So ET. Okay, so notice that guy is coming down, right? So if I start to draw this, my first line is going to be pointing down, and I'm going to have ET. Now, if I'm, again, looking at this, and I'm rotating my body here to actually try to depict this a little bit better, as we look here, we have the dash going into the board, and so in my handedness, that dash is something pointing up and to the right, right? Into the board right now is right, so that dash is a methyl group, so we can write that methyl group, and then we do have a hydrogen, right here, hydrogen. As I rotate my body, that hydrogen is pointing up into the left for me, right? So we would draw this up into the left, okay? So now we're still looking down this bond axis. On the other side, on our back carbon, which is this carbon, we've got hydrogens that are implied, right? So we can draw them in if we want to, or just note that they're there, and they're both going to be pointing down into the left and right. And then we've got this group up here, which is 1,2 carbons. So 1,2 carbons, which again is an ethyl group, right? So we can write that as CH2, CH3, or we can write that as just ethyl. So we're going to go ahead, we'll draw that back carbon. That ethyl group is now pointing directly up as we're looking down at it. So this is an ethyl. And then we've got a hydrogen and a hydrogen. Okay, so then finally, we've got this guy. the bond that we're looking down is right here. Our front carbon, we have a methyl group pointing up. So I'm going to go ahead and draw that first. So we've got methyl pointing up, and then we've got this bromine that is pointing down. And as we look at this, it's coming out at us, so that is to our right at this point in time. So this guy is down and to the right, and then we have an implied hydrogen that's down and to the left. Okay, so then we're looking through towards that back carbon. This guy's our back carbon here. Again, we have a methyl group. This time now, though, as we're looking through this, it's pointing down. So we'll write methyl here. We have a chlorine that's going into the board. As we're looking at that into the board is pointing up into the left. And then we have that implied hydrogen that's coming out at us that's pointing up into the right. So this would be the correct Newman projection for this guy, okay? So again, this whole left-right thing is important, so make sure to orient yourself in whatever way they want you to look at the bond axis. That's important. And again, they could say this in a different way. They could say, for this one, for example, looking down the C3 to C2, or however they want to go about trying to tell you or inform you what bond to look down and how to look down it, which hopefully will make more sense when we go through a couple more of these. In theory, they're going to at least allow us a nice, easy way to assume or see the various conformations that our alkanes can take on, okay? So what do I mean by that? So first thing I should note, all of our alkanes, what type of bonds do they have? What type of bonds are these carbon-carbon bonds, carbon-hydrogen bonds? So they're all single bonds, right? What type of bond is a single bond? A pi bond or a sigma bond?
Sigma bond.
Sigma bond, okay? So remember, sigma bond formed via head-on orbital overlap, right? And so because of that head-on orbital overlap, that allowed free rotation about that sigma bond, okay? So all single bonds are freely allowed to rotate. They can all rotate 180 degrees, 360 degrees, etc. Do we get the same thing with pi bonds?
No.
No, because with pi bonds, we had that side-on orbital overlap, right? That if we started to rotate it, it would break that orbital overlap, okay? So that's the first thing to note. All of these bonds can rotate, okay? Now, with that, what we're going to be really, really, really interested in is these various conformations that our molecules can take on because these bonds can freely rotate, okay? And that's what the Newman projection is supposed to allow us to see easily, as opposed to trying to draw it and wedge and dash and rotate it weirdly, etc., okay? Okay, so there's going to be a couple of things that we're going to define. The first thing is what is called the dihedral angle, okay? So the dihedral angle or the torsional angle is essentially the angle between whatever group we're interested in on the front carbon and whatever group we're interested in on the back carbon, okay? This is not an angle between carbons or between groups on the same carbon. It's whatever we're interested on the front and whatever we're interested on the back. So right now, this guy and this guy is going to define our dihedral angle. This guy is on our front carbon, this guy's on our back carbon. What would you say that angle is about right now?
45, 30?
They say it's about 60 degrees, right? So in this conformation right now, the angle between these two is about 60 degrees, okay? If I remember how to draw a degree sign, okay? Now, what can this be, right? This can be anywhere from when they're completely eclipsing one another, right on top of one another. This is 0 all the way to 180 degrees. So our dihedral angle can be anything from 0 to 180 degrees, okay? Now, depending on what this angle is going to depend on the various conformations that we can look at with respect to our little ethane molecules or our little alkanes in general. But again, it's this bond rotation that's going to allow us to see these various conformations. So now let's talk about two of them in particular that are very, very, very important with respect to looking at the energies of these molecules. Okay, so we're going to start with ethane again because it's the easiest one to look at. The two conformations that we're super, super interested in is what is called the staggered conformation, right, where all of the groups on one carbon are staggered and offset with respect to the back carbon, right? So in our Newman projection, this is our staggered conformation, right? Everyone's completely offset. We have a dihedral angle of 60 degrees here. So this is 60 degrees. The other conformation that we're particularly interested in is what is called the eclipse conformation, okay? So in this conformation, all of the groups on the front carbon are eclipsing the groups on the back carbon, right? So what does eclipse mean?
It's overlap.
It's when they completely overlap, right? What is an eclipse whenever in astrology or whatever? It's when, yeah, it completely covers the sun or whatever happens, right? So again, all of the groups are completely eclipsing one another. And when we draw that in our Newman projection, we can't draw it directly as they are, but we do draw them just slightly offset, okay? So everyone is eclipsing everyone in our eclipse conformation. This would be a dihedral angle of 0 degrees at this point. Okay, so we have this guy. We're going to start by talking about the staggered conformation. I've already written kind of what, with respect to energy, with either of these two are, but who do you think would be the lowest in energy? Who do you think would be more stable in a staggered or in an eclipse? The staggered conformation. Okay, so long term, our staggered conformations are always going to be lowest in energy, whereas our eclipse conformations are always going to be highest in energy. Okay. Okay, so we're going to start with our ethane molecule, right? And we're going to start looking at the energies of these various conformations when we start with a dihedral angle of 180 degrees, okay? So if we look at the energy diagram for this guy, and we start down here, we have a hydrogen on our back carbon and a hydrogen on our front carbon, 180 degrees with respect to one another. So they're going to start in the staggered conformation, okay? As I start to rotate one of these guys, what are they going to start to move into? The eclipsed, right? So if I start to rotate this molecule, we'll see an increase in energy as I move into my first eclipsing position. But what's going to happen as I continue to rotate? We're going to go back to staggered, right? So staggered, and I continue to rotate. We're going to go back to eclipsed, and I continue to rotate. We go back to staggered, and then we end up back to where we got to originally, okay? Now note, is there any energy difference between either of my eclipse conformations at all? No, because in each of these, how many things are eclipsing one another, and what are they? Each of these has hydrogen and hydrogen eclipsing, and there are 3 of them for each of them, right? So each of our eclipse conformations has these hydrogen-hydrogen eclipse, hydrogen-hydrogen eclipse. So these guys all have the same energy, okay? What do we call that when we have the same energy level? Or things have the same energy, we call that degenerate, right? So anything that has the same exact energy level, those are all degenerate energy levels. So these are all degenerate conformations. Now, that's the eclipse energies, right? So we have 3 hydrogen eclipse in each one. Again, those are all equal in energy, so they're all degenerate. What about our staggered conformations? Do these guys differ with respect to one another at all? No, right? So they are also going to be degenerate. They're all equal in energy. And we can actually measure the difference in energy between the staggered and the eclipse conformation. It ends up being about 12 kilojoules per mole. Okay, so this is known. This is an actual value. So why? That's kind of the big question. Why is there an energy difference here? So people used to like, this has actually changed since whenever I was in college, people used to like to say, okay, when we move into the eclipse, and we'll bring this up again, we move into the eclipse, right? You've got a bond here, it's got some electrons around it. You've got a bond here, it's got some electrons around it, right? So when they move into eclipse one another, maybe those electrons or those electron clouds kind of butt up with respect to one another. So people always used to like to say, oh, this is steric strain, right? We've got an electron cloud here, an electron cloud here. When they eclipse, they're going to repulse one another. That's going to increase the energy overall, okay? In reality, though, with respect to ethane, this isn't true. Because, again, these are just hydrogens. They're very, very, very tiny, right? So they're not going to actually have anything to do with sterics. Instead, it goes back to molecular orbital theory, okay? And what they find, and this is newer, so that's why it's in this newer textbook, is that the staggered conformation, what we find is in the molecular orbitals of our staggered conformation, we get orbital overlap between a bonding molecular orbital on one carbon and an anti-bonding molecular orbital on the other carbon, okay? Anytime you get orbital overlap, it allows the electrons to kind of diffuse themselves and spread out a little bit more, which is just particularly stable, okay? So the reality of this is the staggered conformation is energetically stable because we do get this orbital overlap in the bonding molecular orbitals, okay? When we move out of that, we break that stability, and that's why we see this increase in energy as we move into the eclipse conformation, okay? Now, most important though, we can calculate how much each of those hydrogen-hydrogen eclipses cost, because we know that the difference in energy between the staggered and the eclipse is 12 kilojoules per mole, okay? So if the total energy is 12 kilojoules, and in that eclipse conformation, how many hydrogens actually eclipse one another? We get 3 sets of those hydrogen-hydrogen eclipse. So because of that, this guy divided by 3 is equal to what? About 4, right? So each of these hydrogen-hydrogen eclipses, we can approximate to be about 4 kilojoules per mole, okay? So again, this is a hydrogen-hydrogen eclipse. This is the energetic cost. Okay, so then also one thing to note too, that whole energy penalty as we move into the eclipse, we call that torsional strain. It just has a name, it's torsional strain, and we'll refer back to it when we talk about another type of strain that we see in some of these conformations. Okay, so we're going to go ahead, we'll stop here with ethane, we'll come back on Wednesday, talk about propane and butane and the various energies that we get with them as well. Yes?
So is staggered also then dihedral?
So the dihedral angle refers to any position. It could be staggered, eclipse, doesn't matter.
Okay.
But in the staggered conformation, that angle is usually 60 degrees.
Okay. So but just the eclipse has a torsion.
Just the eclipse has the torsional strain, yes.
So the quiz is going to have the Newman and the Newman?
Newman naming, yes.
And also the end of chapter 3, the leveling factor?
Maybe, yeah, probably, yeah, we did talk about that. Or at least the protonation. I won't talk about leveling effect. But can this thing protonate this thing? That could be on there, yes.
Okay.